Just, I'm recording my my screen here, but I think your voice would probably be recorded too, just so you know. Okay, so let's get a new slate here, and we'll just go through them in the order, and you guys are welcome to just say, hey, can you do that one more time, or whatever.
Hi, Professor James.
Good morning, how are you?
Good, how are you?
Tired.
Yeah,
Fridays, right? Okay, let's see. Homework 2, let's start there, and then we'll go to homework 1. All right, let me pull these up real quick. Seems everybody wants a review session today, so I just did 101, and then after you guys, I have 111. So yeah, going nuts. Okay, homework 1. I'm sorry. I guess we're starting with homework 1. I lied, so because that's the one I pulled up. So we'll do Cyrus' questions first. All right. Let's see. We have number 8. Draw an isomer. Okay, let me just write it out. So we have C6H6N2, and we have no sp2 carbons, I think. So with this, oh wait, we definitely do not have 6 carbons. I don't know how to. There we go. Alrighty, am I showing the right screen, by the way? Am I showing you like my chalkboard thing?
Yes.
Okay, cool. I have this kept switching between canvas for the last class, so cool. Alrighty, so with this, we have some options here. And is this it's got a 5-membered ring. Okay, we do need a 5-membered ring as well. So a couple things we should probably remember is that we can't ever have kind of hydrogen as part of a ring, right? Because hydrogen can only ever make one bond, so hydrogen always is going to be something that sticks out. So with this, kind of we have some options. We can have it kind of like this. We have our 3 carbons and 2 nitrogens, or we can have the nitrogens touching each other.
Oh, it's number 9.
Oh, am I doing the wrong one?
I don't know which one.
Oh, I totally did. Oh, I see. Okay. Oh, okay. So number 8 actually is so you copied question 9, but you wrote question 8. So, you want to do number 8 then?
No, that one, please.
Okay, this one then. The 5-membered ring, no sp2 carbons. Okay. Okay, so we kind of have 2 places to start here. We have to have our carbons and nitrogen as part of the ring because we can't have hydrogens. We have no other atoms to work with. And with this, we have to think, okay, let's just try putting hydrogens on all of these to see what we can do. If we just throw hydrogens out everywhere, we see we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, which means that we have a problem here. And if we try and say, okay, let's get rid of 2 hydrogens and put a double bond, that would work, except we now have violated the no sp2 carbons rule, right? Because as soon as we put a carbon with a double bond, we have now problems. So that one is not going to work. If we throw the hydrogens on this one, we see here again we have 8. But now something we can do, remember a double bond is essentially going to take the place of 2 hydrogens. What we can do is make our nitrogens have the double bond. And because the double bond is entirely nitrogen to nitrogen, there's no carbons involved with that, we are not going to violate the rules of having sp2 carbons. And so this is going to be kind of the structure that you should probably end up with if you do this. If you want to go super crazy, no, you can't because it has to be a ring. So never mind. So that's going to be that.
I totally overthinking that. When I see sp2, that's all I read. So I was like,
oh yeah. It's got to be carbons. So yeah. Yep. It happens. Alrighty. Do you want to also go over number 8?
Yes, please.
Okay, sure, we can do that too. Okay, so we have then a non-cyclic one, so it's, I think, same formula. So we have now non-cyclic, and we have, in fact, interconnectivity of NCCCN. Middle CC unit does not have a bond angle of 180 degrees. So that means if it's not 180, that's kind of our only other thing, right? We just have to have it cyclic with this kind of connectivity, and then the middle unit, this has to not be 180. I don't know how to say not 180 there. Oh, unequal to, there we go. So as long as that's the case. Thankfully with this one we have a lot of options. There's going to be quite a few answers that can work with this one. So I'm going to tell you a little secret. Just so you know, this compound above has the same formula. It had one double bond and one ring. A chemical formula, we're going to learn this later. It had one double bond and one ring above. The same chemical formula can be written linearly with two double bonds or a triple bond. So just a hint for us here, we have kind of two pi bonds to work with. So we can either have two double bonds or we can have a triple bond somewhere. And our only thing is that we can't have the middle carbon, the three carbons can't have a 180 degree angle between them. So right now, as written, the formula is not right, and we're missing some hydrogens. If we put out all our hydrogens, just do that. We see here we're going to have 10 here. And that's our hint, we're going to need two double bonds, right? Each double bond takes away two hydrogens. And so we need 6, we have 10. So we're going to want to put two pi bonds somewhere. And again, that could be a triple bond or two double bonds. The only thing is we have to have that middle carbon essentially be sp2 or sp3. And so we're going to see there's a lot of ways to do it. We could say, okay, if I want that, I can maybe say, how about I do this one? 1, 2, 3, 4, 5. If I do that, and I draw in all my hydrogens, we see that this carbon in the middle here is sp2. Just so we are clear, that not 180 means we're looking at sp2 or sp3. And we're going to see we can come up with structures where either one is the case. In this case, I'm putting it as sp2. If I put my hydrogens on, we're going to see we indeed have 6. So putting two double bonds in this molecule will get rid of 4 of those hydrogens. We end up with 6 overall at the end. We have our middle carbon as sp2, so we are good. That's one way to do it. We could alternatively do it another way. One, two, three carbons. We could have a triple bond to nitrogen with this carbon right here. That means this carbon now in the middle is sp3, which we are totally allowed to do. If we draw in our hydrogens, we're going to see we indeed have 6 here. So either one of these could work. And you could, I mean, it's equivalent if you put the triple bond to nitrogen on the other side, or if you like switch stuff around here. We just have to have two double bonds or a triple bond in this molecule. And we just have to make sure that that middle carbon is either sp2 or sp3 hybridized. So we're looking at either it's got a double bond or single bonds only.
Okay, thank you.
All right. Cool. Okay, and then 12B and C. Alright, 12B. I'm glad it's not one of these ones with all these crazy functional groups. Look, I'm not going to draw that. Okay, so 12b, or 12b, yeah, let's start there. So 12b, we are asked to choose the strongest acid and the weakest acid and kind of then draw the reaction between them. Or sorry, we're drawing the strongest acid and the conjugate base of the weakest acid. So 2 parts here. We've got to first figure out the strongest acid, and then we've got to decide our strongest and weakest, and then we'll deal with the reaction. Okay, let's do it. So if we're comparing these acids, what we want to do is look at the conjugate base. So I'm going to just get rid of the protons. And we want to kind of address this in the order here of the cario, or even just ario. We don't have any cationic acids here, so nothing with C. Next is atom identity, right? That the hydrogen is on. So what we want to do is look at these atoms and see, okay, which one is going to be the best at accommodating that negative charge. And remember that for atom identity, the most important factor is size. And then after that, then we deal with electronegativity. And so for size, we're looking at which period in the periodic table these are in, which row. And so if we are comparing nitrogen, oxygen, and sulfur, we see nitrogen and oxygen are in period 2, sulfur is in period 3. Therefore, sulfur is biggest of these 3. And so that means that sulfur, this one is going to be our strongest acid, the one that the SH on it. After size, then we look at electronegativity. So because oxygen and nitrogen are in the same period, their sizes are somewhat similar. Nitrogen's a little bigger, but when they're in the same period as each other, that's when we look at electronegativity instead. And so we say, okay, oxygen is more electronegative than nitrogen is, so oxygen is better at accommodating that negative charge. So that means nitrogen is worse at accommodating that, and therefore it's the least stable conjugate base, which means it's the weakest acid here. Does that part make sense? Cool. So we're just kind of comparing those here. We don't have to worry about the rest of the RIO stuff because we found our point of difference was the atom identity. So with this, we have our strongest acid. And I'm going to actually draw it a little bit differently. And then we have our weakest conjugate base. I'm going to draw this one flipped around. It's just going to be a little bit easier. So those are the two. We have our strongest acid, and we have our essentially strongest conjugate base, or it's the conjugate base of weakest acid here. And so the mechanism, how the arrows will push, you always, again, will start at a lone pair or a bond. For acid-base reactions, we're always going to pretty much start at a lone pair. So here we go. We're going to go ahead and have this nitrogen grab that hydrogen, and the electrons from that bond are going to go on to sulfur. As a result, we end up with sulfur with now an extra lone pair. That single bond to hydrogen became a new lone pair. And now the nitrogen will have used its lone pair to make another bond to hydrogen. And so the benzene bonds don't change. They're really ugly, but that's okay. And in fact, just for clarity, I'm going to make this hydrogen green. So that's the hydrogen that has moved now over. So the acid-base part of this reaction is the moving hydrogen. Okay? So that will be that. Okay. part C then we can go ahead and look at a little bit different here. Oh, any other questions on this one, by the way, before we move on to the next?
No, thank you.
Okay, cool. All right, 12B, or C then, sorry. Okay, so we've got ammonia. We have got, I'm going to draw this just a little bit differently because why would we ever draw it that way? Okay, and then we have C double bond O, NH2. Okay, so with these, we have a couple things to look at here. If we look at our Cario, this is, in my opinion, probably the most difficult of the ones that are given to us here. We'll go through it. We have no cationic acids, so not applicable. Let's look at atom identity. All of the hydrogens on these molecules are all attached to nitrogens, so they're all attached to nitrogens. There's no difference in atom identity. Let's look at resonance. Do we have any resonance here? Aha, potentially we do have resonance, right? We see, how do you know that? How do you know there's going to be resonance? Kind of indicators for resonance are we have double bonds in some of these molecules, so that chances are they can resonate. And so let's go ahead and look at that. So maybe this will come down to resonance. So if I take a hydrogen off of each of these molecules, I'm just arbitrarily choosing one. Oz in the meantime, I don't know if you can hear him, he's like grumbling about something. He's just sitting in the, okay, he's sitting in the window getting mad at his like shadow. Okay, anyways, so I've just gone ahead and taken off a hydrogen off of all of these to look at their conjugate bases, because again, that's where we make these determinations about what's the strongest. So if we want to resonate, good place to do is start at your negative charge and resonate away towards a double bond. That's usually a good idea. So with our first amide ion, we have no resonance, right? We just have single bonds to hydrogen. We have no resonance here. No resonance on this molecule. But with these ones, we can resonate. We can go form a new double bond and break a different double bond in each of these. If we draw the resonance forms. So this nitrogen had one lone pair. We've now given it a second one, so now it has the negative charge. And if we look at the next one here, we have now moved our negative charge onto the oxygen. So oxygen had two lone pairs to begin with. We've now given it a third one by moving those electrons around. And so now we're going to look at these. So what we want to do is see, okay, does this resonance help? Does it do nothing? Or does it make it worse? And so some resonance, by the way, is always better than no resonance. Even if your resonance forms are worse, there is still some resonance, and some resonance always wins out over none. Because even if it's a bad resonance form that you get, you're still moving electrons around. So you're still distributing that electron density. If you can't resonate at all, then you have no way of kind of sharing that burden, even if it's just for a fraction of a second. Anyways, so this is going to be the worst one, the weakest, by the way. Just because it can't resonate. This ammonia will be the weakest for sure. If we're looking at the other two, though, we're now looking at their resonance forms. And so with this resonance, we're saying, okay, well, which one's better? This middle molecule, we've moved our negative charge from nitrogen onto nitrogen. essentially making the same molecule. And with the next one, we've moved it from nitrogen onto oxygen. And we see, that's better. Remember, oxygen is better equipped to handle a negative charge than nitrogen is, because oxygen is more electronegative. So, because oxygen is more electronegative, we're going to see it's going to be the better resonance. So, first thing you're asking, can everything resonate? If only one thing can resonate, that's always the strongest. If two things can resonate, you have to then look at which one has the better resonance, which one will stabilize the molecule more. And so in this case, it'll be that one with the oxygen, because we're moving a negative charge onto oxygen. That's better than moving a negative charge onto nitrogen. So we're going to see here that that's the better resonance. So therefore, this will be our strongest. And then we have that middle one will be in the middle. And if we draw the acid-base reaction, hold on, let me do this. So, okay, so if we just redraw the molecule, and then we have, what else? That was the, so if we have this, again, I'm going to draw our nitrogen in a different color. Again, we start at the lone pair, we attack the proton and push the electrons onto the atom. We could resonate it, in fact. We could say, we could say, in fact, what's going to happen here is that's going to make a new double bond. We're going to push those electrons up. That's actually probably what's more likely going to happen. Because the resonance favors the oxygen having the negative charge. So we could draw it that way. I would be okay with either way. But we're going to see here we get, I'll draw it with the oxygen with the negative charge. If you left it as the nitrogen, again, not a problem. And then we have ammonia then at the end. Okay? So this one came down to looking at their resonance forms and seeing which one was better.
For the first part on the cation part, it might be like really easy question, but how do you tell that?
All right, here we go. Compare these three. If we're comparing the acid strength of these, which one is like kind of most easily able to lose a proton?
Is it?
Should be the plus one, right? Because if we look at this guy, we have a positively charged nitrogen here. It's going to be very easy for this to lose one of its hydrogens. We could say, okay, something else here. I don't know, maybe hydroxide, whatever. Some base comes in, kicks it out. And we end up making ammonia and water. If we compare this to this, the ammonium to the ammonia, we see that this is actually the more stable one. We actually have our conjugate base is more stable than the acid. And that's not something you can say for many of these. Like with these last ones, like they're just happy to be regular. They don't want to necessarily be acids. Like they don't want to be charged, right? They would prefer to be neutral. And so neutral things are always more stable than charged things are. I'm sorry, where am I? There we go. So when we're looking at this, we're forming something that's neutral from something that's charged. a cationic species will always be a better acid when you're comparing the same things. If that makes sense.
And because none of them had like charges on them, they couldn't do like a different like they couldn't do like a resonance. I mean not resonance. How do I say this? Like they can't react to it, something, right? Because or like they're more stable. But then these can react, right? Like the one that you said can donate the proton.
Well, I mean, if we were to pretend these could all react, we could see what's the 3 conjugate bases we get. If we look at this one, if I just go ahead and just put like base, whatever, if we just lose a proton, we now have this. And if we take the last case and we somehow do this, if we're comparing now, just looking at these 3 things, which is the most stable of these 3 things? Well, just regular ammonia, right?
Yeah.
Neutral. And then the second most stable would be the single minus charge. And then the worst one of all would be the 2 minus charge, right?
Yeah.
So that tells us that this is the strongest acid, which leads to the stablest conjugate base. This is the medium acid here, and then this will be the weakest acid of these 3. So that's what I mean by cationic, is if we're looking at the same thing, a positively charged acid is going to be much stronger than a neutral acid. Because it's already unstable, it's ready to react, it's going to make something that is neutral. And so that's going to be very favorable.
Okay.
Okay?
Thank you.
Sure. All right. Let's go ahead and let's look at the homework 2 ones. I want to make sure I get those in here before we have more. Okay, so we're doing that sort of thing. Okay, let me pull up homework 2. All right, so question 7. Let's do that one first. Question 7. Provide the IUPAC name for compound number 2. Okay, 7.2. Okay, 7.2. So I'm going to try and draw this. We have chlorine there, hydrogen, hydrogen, hydrogen. Yeah. Hydrogen and then hydrogen, hydrogen. Okay. Okay, so if we want to name this thing, probably the first thing we want to do is just get rid of all these hydrogens because they're just in the way. So I'm going to do that. We don't need to deal with those hydrogens. They're just going to potentially confuse us. So, ta-da! This should make it a little bit easier to name, I think, getting rid of the hydrogens. At this point, we have not learned, actually this is not a chiral molecule anyway, but what we want to do is first identify the parent chain. Our parent here is going to be this 4-membered ring in green, which we call cyclobutane, right? 4-membered ring is cyclobutane, that's our carbon parent here. And then we know that either of these we could start numbering at. We're going to end up with 1 and 3 anyway. And so if we did this, we'll say, okay, on chlorine 1, I have a chloro. I'm sorry, on carbon 1. On carbon 3, I have a chloro. So if we want to put these together, we'll say 1,3 dichloro cyclobutane. And if we really wanted to be extra informative, we would say that this is trans 1,3-dichlorocyclobutane, indicating that those chlorines are the opposite side of each other. However, this is not an IUPAC way. We don't say trans for this. We have a different way to talk about what this means. That we'll learn in the next chapter. So, like, I'd be okay if you wrote trans. I'd be okay if you didn't write trans. So, either way, I'm happy if you just write 1,3-dichlorocyclobutane. So, but if you put the trans, whatever. Yeah, go ahead.
So if they have like a bunch of, because all those questions on 7, like they have a bunch of hydrogens on it, like you can just take those off. So
yes, pretend they're not there. Make it easier on yourself. Because nobody's going to say dihydro or whatever. Like, no. We just assume the rest of the hydrogens are there. So, yeah. Easiest thing to do is just get rid of hydrogens and, like, names that they like number 4. So.
What about if they're attached to, like, a carbon, then you have to keep them, right?
What do you mean?
If it's, like, CH3 or...
like, so something like this. If I were to throw that on there.
Yeah.
If you want, you could just say, okay, well, I'm going to just put it like that. And leave it as an unwritten carbon. You could write CH3. That's okay. Because, like, you're still understanding that's a methyl substituent. So, it's... Go ahead.
Oh, no, nothing. I was just saying, so just leave it. If it's like a methyl or something, like, we can just leave it like that.
Yeah. So if you look at, like, 7.4, I guess, you see we have an ethyl group sticking out of the cyclopentane. So you can just leave it like that, or you could, like, if it was just one carbon, you just have a single line coming out instead of like that bent thing. Like on number 16, actually, you have a methyl group pointing out, or on number 50, you've got methyl groups there. So yeah, but on number 19, it's written out. So either one is okay.
I have a hard time like identifying if it's written like that, like on number 4, like what that is.
Yeah, so that's an ethyl group. So, yep. And that just comes with practice. So, believe it or not, the hardest thing is actually counting carbons. Like, believe it or not, that's the biggest mistake students make, especially once we get in reactions, is all of a sudden new carbons will just come out of nowhere. So, when you're, like, doing reactions and stuff, or redrawing molecules, like, always count your carbons. Make sure you're not adding extra or forgetting any. And so, like, if you kind of write out numbers on those, you'll see, oh, okay, I have 2 carbons there sticking out of that cyclopentane. And so that's an ethyl group, yeah. Okay, let's take a look at the next one, which is number 8. Okay, which I don't think has any subparts. It's just yeah, okay. Alrighty, 2-methylbutane. So, first thing, can we draw that? So that's 2-methylbutane, right? Actually, let me draw like a little barrier here. So this is number 8. This is 2-methylbutane. So first part of this is, can we draw the correct molecule? And that's kind of the first test. So now what we want to do is look at, we're going to draw a Newman projection looking at these 2 carbons, right? Because this is carbon. Like, if we were to number these carbons, we're looking at 2 and 3. So, here's our eyeball. We're looking down this way. If we want to draw this, we can. Our front carbon, actually we should write methyl for these. We could write CH3. That's also done for Newman projections, but the other ones, when we start hitting the ethyl, propyl, we use abbreviations. If you use CH3, it's fine. I'll do it. I'll use CH3. We have 2 methyl groups on carbon 2, as well as a hydrogen. Right? Those are the 3 things that we have on carbon 2 that's not carbon 3. Carbon 3, because we know that one's the back part. On carbon 3, we have a methyl group and 2 hydrogens. So, are we okay getting to the Newman projection from this molecule?
Kind of like the first part where we draw out the line structure. I'm kind of confused, like for methyl butane, how to kind of draw it out. Because I know like it's gonna have single bonds, right? Because of the A and E, and then is that 5?
Butane is 4. Bu is 4.
4.
Yeah.
4, and then, so that would just mean I need to make sure I draw out 4 lines, right?
Mm-hmm. So you'd have,
Or 4.
this is butane right here, right? This just like lightning bolt looking dude. That's butane. Or if you want, you could like totally like, if it helps you, if you want to write it out this way first, if this kind of works for you, and then you can draw, now I've got a methyl group on carbon 2. In skeletal structure, you'd say the same thing. Okay, I've got my 4 carbons, and I'm going to draw a methyl group on carbon 2. And so,
because it says it's between carbon 2 and carbon 3?
Mm-hmm.
Okay, so that's where I draw the...
So that's where we're looking between.
2, okay.
Yeah. So the 2 methyl tells us it's on carbon 2, right? So this means
between 2 and 3.
Oh. But that's what our Newman projection is looking at. So 2 and 3 is looking at what's on our Newman projection. So this front dot is carbon 2, and this back circle is carbon 3.
Oh, okay.
That's what I mean by that.
Really looking at it like in a really...
Oh yeah. So sorry. So 2-methylbutane is the name of the molecule. And then whenever we do a Newman projection, we always are looking at 2 carbons, right? We're looking at a front carbon and a back carbon. And so we need to just kind of identify those. So for this one, I'm looking at carbons 2 and 3 along my Newman projection. Okay?
Okay, thank you.
Cool. So now let's go ahead and do these rotations for this. So if we rotate this, again, typically we're rotating 60 degrees. Can go either way. What would you like to do? Counterclockwise or clockwise, and which carbon would you like to rotate? And we'll do it that way.
Whichever way that you
choose one. Well, they're all going to be essentially the same. We're just going to have them in different order. So
I can just choose like any carbon, like whether it's a C2 or C3.
Yeah, you can choose to rotate either carbon, the front or the back.
Okay, I guess we could rotate C3.
All right, so we're going to rotate the back carbon. Do you want clockwise or counterclockwise? All the choices.
Clockwise?
Clockwise, okay, sounds good. You'll see on the practice exam, some of them I've said rotate the back one 120 degrees clockwise, whatever. So I'm letting you choose here because we're going to get all the angles. So we're going to be rotating the back carbon 60 degrees clockwise each time. So we're going to be taking that carbon and rotating it. So everything on that back carbon is going to be rotated as we go along. So if we draw the next one, and 60 degrees means just things that were in between are now going to be kind of eclipsed, right? We go from staggered to eclipse every time we rotate by 60 degrees. So if we do that, I'm going to keep my front carbon identical. We're not touching the front carbon here. And in fact, for ease of copying, I'm just going to copy this and we're going to paste it many times because our front carbon isn't changing. The back carbon is. So if we draw this, I'm going to use blue for the things on the back carbon. So we have now that methyl group has moved to the right. That hydrogen has moved now down. And the hydrogen that was on the left has moved up. And so that's our new kind of conformation. And if we keep rotating 60 degrees, we rotate some more, keep rotating. I'm going to just draw all the structures first, and then we can look at their kind of what we expect to be higher energy, lower energy. So if we keep rotating, we now have moved things around. We have now moved our methyl group in now between the other 2 methyl groups. If we keep rotating, now we're going to end up putting them behind each other. I'm gonna have to start this one down here if that's okay. So
How do you know when to stop rotating them?
once we get back to our original structure. So we're going to end up with 6 things. So, because so a circle is 360 degrees, right? And so 60 degrees means we're going to have 6 total like structures as we draw it. It's a totally valid question. If you keep rotating past 60, you're going to start duplicating things. I'm sorry, past 6 times you start duplicating because then you're past one full circle. So we just want to do one full circle. Okay? So if we were, go ahead.
Oh no, I said that makes sense because it's 360, so it's going all the way around.
It's going all the way around, yeah.
Okay.
So I'm just now moving all these things. Okay. So once we rotate them 60 degrees again, now the methyl is blocking the other methyl. And we keep rotating a couple more times. Oops, let me move that up.
I'll definitely need to color code these when I'm doing it because it's hard to keep track.
Oh, I totally know. I totally get it. And you may even want to like draw your hydrogens on the back carbon in a different color, just so you're clear of like which one's moving where, or like you could label it like H1 or something.
It took me a moment to realize like, oh right, the front ones, they are like connected to that part, to the original dot, and then the outside with the circle are the back.
Yep. Thing on the circle are the back ones for sure. So I'm going to actually draw this H in light blue so we can see it moving around. So it's different from the other H. Okay, so if we keep moving it, now that blue H is out here. We now have our methyl group here. And then we have our hydrogen up. And then we rotate yet again. Block that off. Put an H there, and then we have our light blue H. And if we rotate this one more time, we end up with our original molecule where we have the like light blue H in the bottom left. So we see here as we've done this, that light blue H has moved all the way around the circle. Starting in the bottom left, it then moved to top left, then top, coming down top right, bottom, and if we rotate once more, it's going to be bottom left. When I did that shamefully, should be on the other side. Okay. So we see how that light blue H is moving around?
Yes, and then if we move it, like you just said, one more time, it's going to go back.
It goes back to the original one, yeah. So that's why 6 is kind of our magic over here. So, I'm just going to flip this vertically so we can look at all of them at once. Okay, we can do this kind of, okay, whatever. So, now that we see all of them, we want to see what's kind of like the best and what's the worst. And let's go from there.
So if we were to move it, like choose 120, like counterclockwise, right?
Mm-hmm. If you wanted to do that, if you were to move it 120 degrees counterclockwise, that would be going from 1 to 5. If we were to rotate 120 degrees counterclockwise. So do we see how I've rotated? If we look at those two, compare those two structures, we have the light blue hydrogen bottom left. If we rotate it 120 degrees, remember 120 degrees is a third of a circle. So we will have rotated counterclockwise kind of twice, essentially. And we now ended up with the bottom right part of it, if that makes sense. Do we see how 1 and 5 would be a rotation of 120 degrees counterclockwise? Okay, let's look at it here, just on a circle. Here's our line. Here's a circle. If we want to rotate this, remember that a circle is 360 degrees, right? Oh, I'm sorry. I wasn't pushing my
couldn't hear.
I wasn't pushing my push to talk button. I was like,
I was just about to say I can't hear
oh
you.
my gosh, I'm so sorry. Yeah, here, let me put it on. I normally put it on just voice activity. My bad. Let me fix that. I realize I'm like, really? I have to explain 360 degrees? Okay, so. But I was like, what? Okay, so sorry. If you had to rotate it 120 degrees counterclockwise, you're looking at going from number 1 to number 5 there.
Number 1.
Do we
Okay.
see how that's...
It wouldn't be 3 times. Like, I would have to do it 3 times then to equal 360.
If you're doing like the full thing, but if I just asked you to rotate it this many degrees, that's just one time only. So like on some of the practice exams, it's like take your Newman structure and rotate it 60 degrees clockwise. That's just once.
Mm-hmm.
But for something like this where I'm asking you to show all the like energies of these, you're gonna have to do all 6.
Oh, okay.
So, okay?
So if it were to ask us 120,
Then you're just doing it once. Just once.
Once, okay. Yeah. And then if they ask for like a full
circle, then you do it 3 times if we're doing it by 120. But typically we do 60 because that way we go between staggered and eclipsed each time.
Okay.
So,
thank you.
Yeah, no problem. Let's look at our staggered ones, because those are always our highest energy. Our staggered ones for this, I'm going to just label them so we can compare them easily. Our staggered ones are 2, 4, and 6, right? Those are the staggered ones. I'm sorry, those are the eclipsed ones. I am so sorry. 2, 4, and 6 are eclipsed, right? They're the ones that are overlapping. So staggered ones are 1, 3, and 5. Eclipsed ones are 2, 4, and 6. Is that okay? We can identify them as staggered or eclipsed.
Can you explain that a little?
Of course.
I know eclipse is like sideways, right? They're gonna be.
So staggered just means like that we have like kind of a nice gap in between them. Like all the things are 60 degrees apart. Like if we were to draw like an angle here, that's 60 degrees, that's 60 degrees, that's 60 degrees, etc. They're all nicely spread apart. So those are the ones, the Newman projections that look a little bit neater, right? If we look at 2, 4, and 6, those are all clumped together, right? We have everything kind of on top of each other. Those are the eclipsed ones.
Because in the line diagram, right, that we were in the lecture, like the eclipsed ones were like kind of stacked on top of each other.
They're stacked on each other, exactly.
Okay.
And so we're going to see that's the case with 2, 4, and 6 here, that things are stuck on top of each other. And so they're going to be bumping each other. So, if we look at our staggered ones, we can look at those first, 1, 3, and 5. What do we think about those? Remember that, like methyl groups are big enough to still kind of bump into each other when they're staggered. Hydrogens not so much, but methyl groups are big enough. If we're comparing those, first off, 1 and 5 are essentially the same thing. Do we see that? If we look at what's bumping around in this molecule, we have, in number 1, we have kind of 2 methyls that are somewhat close to each other, right? We have the methyl on the back, straight up, and we have that methyl on the front that's slightly to the right. Those two are going to have a gauche interaction, right? They're going to be interacting with each other. We have one kind of methyl interaction in that one, and the rest are all hydrogen-methyl interactions. Do we see that? Like, if we were to just look at what's nearby each other.
The methyl in number 1 is the one on top, right? Like
yeah, the top left there. I'll circle it. That's the methyl. Yeah.
And then the other one, I don't see it in number 5. So.
Aha, it's here. Methyl.
Oh, okay.
Yeah.
Sorry.
No worries. Yeah. So,
I'm on my phone.
No, I totally get it. And also, like, these can be hard to visualize. Like, it takes a lot of, like, 3D brain stuff. So,
it takes, sometimes I'll look at a structure for a while and I'm like, what is going on?
Exactly. So that's why models help. So if anything, just like spinning the model around, you can kind of see these eclipse things
The
happening.
lab helps with
Good.
visualizing,
Help visualizing. Good, good.
how you can turn it on the little hollow thing.
Awesome. I'm glad it did. So yeah, that's the idea. So anyway, so 1 and 5, basically they have one methyl-methyl interaction, and the rest are just hydrogen-methyl. If you look at number 3, though, the other staggered one, we see, we have 2 methyl-methyl interactions. Do we kind of see that?
Yeah. Yeah.
We got 2 of those there. So that's going to be a little problematic, right? So we're going to say that number 3 has higher energy than 1 or 5. 1 or 5 are essentially the same. So they have equal energy, we'll say. Number 3 is going to have a little bit higher energy. So if we're going to draw a graph for this, we'll see number 3 will be a little bit higher because it's got 2 methyl-methyl interactions. All right. Let's look at our eclipsed ones then. What we want to do here is look at kind of what's happening in all of them. Let's look at methyl-methyl interactions in the eclipsed ones now. If we look at the top one, number 2, we have a methyl-methyl.
Yeah.
If we look at number 4, we have 1 methyl-methyl. In fact, 2 and 4 are the same. They have the same type of interactions. 1 methyl-methyl, 1 H-methyl, and then 1 HH. Number 6, though, has 3 H-methyls. Right, these are all, we have 0 methyl-methyls, and we have 3 H-methyls. So we'll probably say 6 is probably the best one of these, the least energy, because we don't have any methyl-methyl interactions.
Oh, so methyl-methyl interactions are always more...
Yeah, so CH3CH3 is about 11 kilojoules. CH3H is about 6. Just giving you numbers on these. And then HH is 4. So methyl-methyl is twice as bad.
Kilojoules were optional to list, right?
Yeah, you don't need to memorize these at all. No worries. But if you were to compare which one's worse, the numbers help, right? You could say, oh, the methyl-methyl is twice as bad as methyl hydrogen. So therefore, having no methyl-methyls is better. And in fact, if we wanted to add these up, we could say 6, 6, 6. We have just all those H-methyl interactions. With number 4, which is the same as number 2, we have 11 there, 6 there, 4 there. We see this adds up to 21. This adds up to 18. So 2 and 4 are going to have higher energy than 6 is. Basically, just look for methyl-methyls, or methyl some other bulky group.
So because the CH3, the methyl group is the larger molecule and has
more bulk. Yeah.
More bulk.
Yeah, and so when they overlap, they are repelling each other more, and so there's a higher energy associated with that.
Oh, okay.
Okay, so with that, we're going to say, okay, 2 and 4 are above 6 in terms of energy. And if we wanted to calculate it, we'd see it's 3 kilojoules more energy. But let's go ahead and we just have a few minutes here for my next review. Our eclipsed ones are always higher than staggered in terms of energy. So eclipsed is always more than staggered. So if we want to draw kind of where these would end up, let's look at them. So we have eclipsed ones are 2, 4, and 6. And we saw that 2 and 4 had higher energy than number 6 did. So maybe we'll draw 2 and 4 up here and number 6 maybe a little bit lower. So remember, energy is always our y-axis for this. So 2 and 4 have equal energy. 6 has a little bit lower. And if we look at the staggered ones, staggered are always lower, but we saw that 3 had more energy than 1 and 5. So 1 and 5 are going to be our low ones here, and maybe number 3 is a little bit higher up. So that's how I'm making these kind of distinctions here. And if we were to kind of draw this, then we could now do our lovely, Drawing. Let me go back down again. And this is how we would be able to draw this. So what we were first able to do, identify all our staggered ones and our eclipsed ones. You'll always have 3 of each, right? If you're doing 6,
Yeah.
half and half. We identified that of our staggered ones, number 3 was a little bit worse because it had methyls nearby other methyls. It had 2 methyls next to each other, kind of. And then we looked at the other 2 and they only had 1. So number 3 was worse. So therefore we've put number 3 a little bit higher than 1 and 5.
If it was,
Go ahead.
okay. I'm just gonna, I have to go to work right now.
Yeah.
Thank you so much for the review.
No problem.
I really appreciate it.
Of course.
Bye.
Bye-bye. Have fun at work.
I'll try.
All right.
So if it was 120
Mhm.
degrees, then for the eclipsed and staggered, would like one be staggered, and then like how would it?
Depends what you start with. If you start with a staggered one, then all of them for 120 will be staggered. If you start with eclipsed, all of them will be eclipsed.
Oh, okay.
Because you're skipping over, essentially. Like if you're going 120 degrees, that's 1 to 3 to 5.
Other.
Yeah, it's every other one. Yeah. So if you're 120, they will all be eclipsed or staggered. Okay, and then the last thing, we looked at the eclipsed ones. We know that the eclipsed ones are always higher energy. And if we wanted, we could put the numbers here, but forget it. We're lazy. And so this would be kind of the way we would look at it. Okay?
And so then that kind of shows like a visual of how the energy
is kind of relative to each other as this thing is rotating between 1 through 6. And then back to 1 again.
And when it says like in instructions like draw Newman projections for all dihedral angles specified.
Yeah.
So by dihedral angles it's just talking
That's
about
the 60 degrees, yeah.
Oh, past the 60 degrees?
Yeah, so dihedral angles are essentially the angles that are between the like things that are sticking out of our Newman. So this 60 degrees is the dihedral angle.
Oh, okay. So like pretty much saying every 60 degrees
Yeah.
until we reach.
So this one I should have been more specific, like every 60 degrees, but yeah. Typically we do 60 degrees for these, so. All right.
Okay, that makes sense. I was confused on what that meant. So
Yeah. I get it.
Well, this was really helpful. And
Good.
I kind of wanted to do one of these to see like how you kind of do the whole process and the thinking.
Sure.
Behind, like each.
And we have more time to do that too, because I know in class it's like, okay, I have to get through all this stuff.
When I'm in class, I'm looking at it, but I'm like taking in about maybe 30%.
Yeah, and then you have the rest you're also trying to process from before as well. Like, what did we just talk about with the chairs? And I get it. What are we, 221? I think so.
Yeah.
Okay.
I'm trying to understand it when I'm watching, and then sometimes I see the homework and I'm like,
You're like, oh crap, what's this? I've never heard of it before. No, I get that. It's normal. Don't worry, you're not. That is very normal for OChem. So, all right, I have to go to our next review session, so I'll see you later.